Hello and welcome everybody. Greetings to our worldwide partners, customers, and all others who are interested in this webinar today with the topic, the challenges of analyzing the efficiency of electric powertrains. My very first minutes, just some short organizational stuff so that you know how to react and what to do during this webinar to allow also other people to connect to our webinar yet at the beginning. So during this webinar, you have the possibility to ask us questions. They are anonymous, nobody else is able to read them, so please do so. It's on the right side of your presentation screen in the chat window. As I said, nobody is able to read these chat questions, only the two of us, me and my colleague. Also, you can download the handouts during this webinar and only during this webinar. If you did forget it or whatever, we can send it to you afterwards via email. Just ask us for them. So yeah, that's everything regarding organizational stuff. The topic today, as I said, is the challenges of analyzing the efficiency of electrical powertrains. We are going to talk about default and common power analyzers and the benefits of a power analysis system which is distributed. And at the end of this theoretical stuff, why to use eventual distributed power analyzers, we are going to show you a practical part and some real life measurements, or my colleague is going to show it for you. So now we are at the point just telling you who is now sitting in front of the cameras. The speakers today are Raphael Ludwig today. Raphael, do you want to say something?
Yeah, thank you for the kind introduction. Welcome, good morning. My name is Raphael Ludwig. I'm an application engineer for Devatron, and I'm going to do the technical part of the presentation consisting of a theoretical presentation and a practical session in the end of this webinar.
Perfect. And my name is Ivica Baresic. I'm the business developer and technical sales for Austria. And you see here our contact data. If you have any questions, feel free to ask us. You have the contact data also available on social media and on our homepage as well. So just some short sentence about Tevatron and who Tevatron is. If you don't know Tevatron, we have 120 employees and headquarters is in Austria, in Graz. We have 3 subsidiaries in the world, and we are active in more than 25 countries. We have sold more than 25,000 systems and 400,000 channels, which is making us a know-how expert in the measurement system area. The portfolio is, as shown here, mobile measurement solution or any kind of rack mount measurement solutions to make measurements of all kind of stuff. Power analysis part, I'm not going to talk about it because it's a big part of this webinar, and Mr. Ludwig is going to talk about it. Of course, calibration and services are a huge part, so we are able to calibrate and do any kind of service and support for our measurements all over the world with our partners and our subsidiaries. Once more, please ask us questions in the chat. I'm going to hand over now to my colleague Raphael, and he's going to guide you through the technical stuff. I'm going to join back later to for the question part. So yeah, have fun, ask us questions. Please do so, use this opportunity, and yeah, that's it from my side. Raphael, the stage is yours.
Thank you very much for the stage. And handing it over to me. Yeah, once again, welcome from my side. As I said in the beginning, I will start with a theoretical introduction into the topic of the challenges of analyzing the efficiency of electric powertrains. The presentation will be split up like that. In the beginning, I will talk about the concept and the requirements of common testbeds, talk about the disadvantages of common testbeds in the daily use of a measurement and test engineer. Then I will introduce you the new idea and the new approach of a we call it distributed power analyzer. I will introduce you the hardware concept of a so-called distributed power analyzer based on the Devatron hardware concept. I will talk about the advantages of a distributed power analyzer and conclude with a short summary and do a practical presentation and a practical introduction into a distributed power analyzer as well. Therefore, I have a small test setup on the left-hand side in my office, which I will introduce you afterwards. But now, first things first, we will start with the concept and the requirements for today's common test beds and start with the limitations. Normally, when we talk about test beds for electric powertrains and common power analyzers, the voltage and the current probes are normally connected to one central power analyzer chassis. The power analyzer itself is normally locally distributed from the device under test, locally separated from the device under test. So typically for at least some meters. In the worst case, the power analyzer is even in a separate room, in the control room or in a measurement system room and far away from the device under test. The resolution and the sample rate of the input channels is normally also pretty limited for the voltage and current inputs. In the real life, we talk about a resolution typically from 12 to 16 bits and a sample rate of some 100 kilohertz, and that's it for many common test beds today. The flexibility of the system of the measurement device regarding different types of input signals is also pretty limited. Normally, a power analyzer or a measurement device for testing electric powertrains can acquire voltage and current data or current signals, and that's it. And normally also the number of input channels is pretty limited. So if you want to determine the efficiency in the electrical or in the mechanical domain of a powertrain, it is very often the case that you need several measurement devices for determining the efficiency. Just to quickly give a practical example how today's testbeds for powertrains may look like. When we have the example of a three-phase motor, which is here in the middle, can be seen here in the middle of the screen, which has typically three phases. You connect the three voltage and the three current signals normally to one power analyzer or one measurement unit. And when you are analyzing the powertrain, you also are interested in the inverter, in the electrical efficiency of the inverter normally. So you also have one phase on the other side of the inverter, where you want to measure voltage and current as well. If you are lucky and your power analyzer can acquire data of up to 4 phases, you can connect all the 4 different phases to one central measurement unit, but it is also common that a power analyzer can only acquire up to 3 phases. In this case, you already need a second measurement unit if you just want to determine the electrical efficiency of the inverter here. And on the other hand, you don't only want to analyze the powertrain in the electrical domain, but also in the mechanical domain. So you also want to acquire the torque and the rotational speed of the motor, and therefore you often need also an additional measurement unit for analyzing the mechanical efficiency, and then for analyzing the efficiency of a three-phase motor, you often need already 3 different measurement units, even for this easy test setup. When we talk a little bit about the requirements for which are stated by test engineers today, the device under test shall not only be analyzed at constant running conditions, but also during run-ups, coast downs, and at different load steps. For a reliable power analysis during these conditions, you need a possibility, or the power analyzer needs to provide you a possibility to automatically detect the fundamental frequency of the system for analyzing the power accurately and for determining the power parameters. And as I also said on the previous slide, you don't only want to analyze the device under test in the electrical, but also in the mechanical domain. And even if typical daily use powertrains and motors typically have 3 phases today. The trend in the development departments of engineering companies is clear that also polyphase systems are developed at the moment and will be normal in a couple of years or in the near future. So you also need a possibility to analyze systems which not only have 3 phases, but which also have 6 or even 9 phases. And for being able to always refer to the raw data in the case that the power parameters have a strange trend in the time domain, you always want to analyze the root cause, and therefore you need a possibility to refer to the raw data, and therefore we need, or the power analyzer needs a possibility to gaplessly store the raw data during the measurement and during the power determination. Let's talk quickly about the disadvantages in the daily use, or let's quickly sum them up, of common test beds. As I said in the beginning, there are long wires from the device on the test to the power analyzer. We have typically a limited resolution of the input channels, a limited sample rate, and a limited bandwidth of the input channels. And the power determination itself is often or may be insufficient, and this may result from blind spots due to the windowing and the blockwise calculation of the power parameters. What does that mean? Just imagine you have a system which has a fundamental frequency of 50 Hertz. In this case, the power calculation is updated every 20 milliseconds when you have a blockwise calculation. But the fundamental frequency may not always be constant at 50.0 Hertz, but it may also vary from 49 point something to 50 point something Hertz. But your window for the power calculation remains constant at 20 milliseconds, and this will cause a lack of accuracy. And also we have a problem with missing active filtering algorithms in the signal path of analyzing and determining the fundamental frequency. In every signal path for detecting the fundamental frequency, you have a low-pass filter for filtering out high-frequency components to get a better accuracy for the fundamental frequency detection. It is often the case that the cutoff frequency of this filter needs to be set manually, and a certain cutoff frequency is valid from only within a certain fundamental frequency range. And if the fundamental frequency range is exceeded, you manually have to change the cutoff frequency. And so you can only do a run-up coaster in a very limited fundamental frequency area. And this would be much easier if you have an active filtering algorithm which adapts your cutoff frequency in the signal path automatically. And anywhere where a filter is working, you have a delay caused by the filter, and it is also often the case that the delay of the filter is not compensated, which will also cause an uncertain or inaccurate power determination. And as I also said in the beginning, the number of input channels is pretty limited, so you don't have a possibility to analyze so-called polyphase systems with more than 3 phases. If you want to do so, you have to purchase several individual measurement units. So you will have several data files recorded during the measurement, which will cause or will be time-consuming and complex to post-process several data files and to analyze them. And when we talk about service and calibration, you have additional expenses when you have to maintain and calibrate several devices, and you also have additional costs for training your engineers to different measurement systems. Let's talk about a new approach which will compensate most of the disadvantages, which we call a so-called distributed power analyzer. And I want to talk about the hardware concept which is required for a distributed power analyzer in the beginning, and this shall be done based on the Tevatron hardware concept. The Tevatron hardware concept has a so-called single board architecture, which means that you have separate data acquisition modules which combine the signal conditioning, the filtering, and the AD conversion directly on the measurement board itself. And the measurement board just has a high-speed data transfer interface, which is a PXI bus, and then the digital data is just transferred in the digital domain from the data acquisition module to your measurement chassis with the PC integrated, and all further data processing is done in the software. And the chassis can be equipped with different kinds of modules, and so you are able to acquire voltage data, current signals, sound, vibration, strain, or also temperature, even CAN and video data can be acquired with one single measurement unit just by selecting different data acquisition boards. And all the data in the measurement unit is automatically synchronized and time clocked via an internal chassis clock. So the test engineer never needs to worry about lack of accuracy due to missing synchronization of your measurement signals. When we talk about the power analysis itself, the Demeter Portfolio provides two different power measurement boards, which is the Trion 1820 Power 4 module, which can sample up to 2 megasamples per second for each channel, or if you need a higher sample rate, the Trion 3 1810M Power 4 board is available with up to 10 megasamples per second for each channel sampling rate. You see the detailed specifications here on this slide. I will not talk in detail or too much in detail now about the specifications. The slide is available in your handouts, so please refer for details to your handouts or also to the data sheets, which are available on our homepage, or just ask us in advance at the end of the webinar if you have specific questions about this one, please. On the other hand, the Tevatron portfolio also has dedicated Tevatron power analyzers. On the one hand, it is the so-called Tevatron PA7, which can acquire up to 12 or the signal of up to 12 power phases and sampling each channel with up to 2 megasamples per second simultaneously. It has, or what makes also Demeter Power Analyzer to a power analyzer is the so-called integrated sensor supply for powering your current transducers. So you have 8 inputs here on the front side to power your current clamps or your zero flux transducers, and you don't need an additional power supply rack for your current transducers. If you need more than 12 phases or need higher sample rates, the second power analyzer in the portfolio is the so-called Demeter PA8, which is also a mixed signal power analyzer. It has its input connections at the back, and you can acquire data of up to 16 phases and sample each input channel with up to 10 megasamples per second. And it also has an integrated sensor supply here at the back below the measurement board, so you also don't need a separate power supply rack for your current transducers. And when it's about distributed measurement systems and distributed power analysis, you need several measurement devices and you need to synchronize the different measurement devices somehow. When you only use a Tevatron equipment, you have the possibility to synchronize them over an integrated timing sync source in every chassis, and also output the signal to different chassis to clock several devices, which is called the so-called enclosure sync. And from the third or external trigger and synchronization signals, the system support PTP, GPS, IRIG, or PPS for synchronizing your devices, and the data transmission from device A to device B is done over LAN, so you can use a Wi-Fi network or an existing LAN network for transferring the data between your measurement devices. And just for giving you a specific detail, when we think about the three-phase system which we saw at the beginning, how may a distributed power analyzer look like for this example? You may have a base unit power analyzer here, which communicates with your testbeds, which transfers the data over Skippy or XCP to the testbed, and which is controlled by the testbed by, for example, Skippy commands, and which also can acquire a synchronization signal from your testbed. And on this base unit power analyzer, several so-called distributed elements are connected. And then you can use for example, one distributed element to acquire the 3 phases of your device or of the motor itself. You can use a second distributed element for acquiring the grid power and the grid voltage, and you can use a third distributed element to acquire the mechanical parameters. All these distributed elements can be placed directly at the measurement point, so you can get rid of long signal and long sensor cables. The distributed elements themselves are connected over LAN, over a LAN interface to the base unit power analyzer. So the data from the distributed elements to the power analyzer, to the base unit power analyzer, is transferred over Ethernet, and vice versa. The base unit power analyzer also provides the synchronization signal for the distributed elements to acquire all the data time synchronously. And if your measurement requirements change, you always can reduce the number of distributed elements or always expand your distributed system by an additional distributed element here in this section. And when we talk about central or decentral power and efficiency determination, you have different possibilities to do the power analysis and the power determination directly here on the distributed elements and only transfer the calculated parameters to the power analyzer, or to only do the raw data acquisition here and to transfer the raw data to the base unit power analyzer and do the power and efficiency calculation here on the base unit system. What advantages does such a distributed power analyzer provide the test engineers? On the one hand, you have a power analyzer or the measurement device directly located at the measurement point, and so you have short current and short current transducer wires. When you have short wires, they reduce your EMC troubles, and you don't have any bandwidth limitation, which may be caused by long wiring and long cables and long sensor cables. In addition, you have a time synchronous and an online determination of your mechanical and your electrical efficiency of your device under test, and you always can easily expand or reduce your system, change the system configuration at any time. So in theory, you have an unlimited number of input channels of your distributed power analyzer. Specifically, the distributed power analyzer from Devatron provides you, in addition, with the following advantages: that you have all the data stored into one single data file time synchronously, and vice versa. You only need one configuration, one setup file for loading the measurement configuration on the distributed power analyzer. So you just load your measurement setup on the base unit power analyzer, and the configuration is transferred automatically to the distributed elements. Raw data of your voltage and current signals is gaplessly and continuously stored to the data file as well, if desired, and the power determination is done with an accuracy of 0.04% based on real periodic values, where you have a zero crossing algorithm with an adaptive filter, and automatic cutoff frequency selection with a delay compensation for the fundamental frequency detection. Even if the zero cross is within 2 measurement samples, a linear interpolation algorithm is applied to the signal to achieve a subsample accuracy for the fundamental frequency detection. And the synchronization source is freely selectable. So per default, it is the voltage channel of your first phase, but you can detect the fundamental frequency on any voltage channel of your system, or also on any current channel on your device under test. And the fundamental frequency is automatically detected in a range from 0.2 Hz to 200 kilohertz. And last but not least, you can use a Demeter power analyzer for analyzing and determining the power of systems which may have up to 9 phases. This is done online there as well. To sum up and to conclude with the theoretical part of this presentation, I want to give you a short summary what advantages distributed power analyzers provide you. So distributed power analyzers significantly significantly reduce the cable length, specifically the sensor cable lengths, reduce EMC troubles, increase the accuracy for the efficient power train analysis in the electrical and in the mechanical domain, guarantee an accurate and a time synchronous power analysis, and last but not least are, in our opinion, the future-proof solution for electrical powertrain testbeds. So much for the theoretical part. As I said, on the left-hand side in my office, I have a distributed power analyzer set up, and I have a remote desktop connection to the base or to the main power analyzer here. This window, which you currently see here, is a VNC viewer, and I am now connected over an IP address to this main power analyzer now, which is, in my case, a Demeter A4. And we will now analyze the mechanical and the electrical efficiency of a three-phase motor. Therefore, I have the voltage and current signals connected to the main system here, to which I'm currently connected over a remote desktop connection. And I want to analyze the electrical efficiency of the inverter, which drives the three-phase motor. And therefore, I also measure the voltage and the current of the grid with a first distributed element, which is a so-called trionet, which is just a simple data acquisition front end. And to determine also the mechanical efficiency of the three-phase motor, I am measuring also the vibration, the sound, and the rotational speed directly with a second distributed element, which is also a data acquisition front end. I could also measure the torque with this front end, but I don't have a torque sensor connected to the motor at the moment, so I'm just simulating the torque signal for this presentation. In addition, I'm also measuring the temperature of the motor, and therefore I am using a thermocouple or a temperature measurement module, which transfers the data from the module itself to the measurement unit over an RS485 serial interface. And the base unit power analyzer itself could also be controlled by the testbed and could also transfer the data to the testbed with a Skippy or XTP connection, for example. And the distributed elements are connected and transfer the data over a LAN interface from the front ends to the base unit power analyzer, and the base system, the main power analyzer, synchronizes the data acquisition front ends over the integrated synchronization source, which is provided by any Dev2 or Dev3 measurement system by Tevatron. So much for the theoretical introduction into the system. I also have a camera connected to the system, so I will quickly move over to the left-hand side and show you also the this measurement system in the real life. Now I'm grabbing the camera, which is connected to my measurement system. Here you see my office door and my jacket. And here you see the three-phase motor and the inverter, which is driving the motor, and the voltage and the current signals are grabbed from this panel here. And next to it, you see the Dev2 A4, which is our main power analyzer at the moment. The three voltage and current signals are connected here to the system. And right on the left side, you have the trionet data acquisition front end, to which the voltage and the current signals of the grid are connected to. And once again, on the left side, you have the second trionet front end, which acquires the vibration, the airborne sound, and also the running speed of the system. And my temperature data acquisition module is located here. Now, when you see this here in the office, it is not necessarily a distributed power analyzer, but more or less a locally power analyzer. But please imagine that between all these measurement units, there can be a distance of up to 100 meters, because the data is transferred over LAN from the front ends to the main measurement system, to the base unit power analyzer. And so the distance limitation is more or less the maximum specification of the LAN cable, which is 100 meters. But if you use Ethernet switch in between, you also can expand the distance from between two data acquisition systems to more than 100 meters as well. So much for the introduction into the system itself. I am back here now in front of my PC and again controlling the system over the VNC viewer. And now just as a quick introduction, how the distributed power analyzer is set up in the software, all the configuration can be done from the main unit. You have the overview about the data acquisition channels here in the channel list. You see the 3 different systems and devices which are used. My local node is the Demeter-A4, to which I'm currently connected, and you see the signal inputs of the device directly here. And you have the channel list available, which shows you the input channels, and you see the voltage and the current signals connected here to these inputs. The temperature measurement module is also directly connected to the Demeter-A4, and the temperature engine is available here in the channel list. At the moment, it's approximately 25 degrees. And the USB camera, which I just used for showing you the system, is also available here in the channel list. The front end for acquiring the grid power and the grid voltage and the grid current is called Grid PA, the Trionet, and the channels of the system are available here in the channel list as well. So you see the grid voltage and the grid current here. And the aux analyzer for acquiring the mechanical parameters is another Trionet, and you see the acceleration and the sound data here in the channel list. And this is the channel to determine the engine speed and the rotational angle of the motor. So much for the input channel configuration and for determining the power. You have 2 separate power groups here. One power group for calculating the electrical power of your engine. Just show you quickly how it is set up. So you have different schematics, which can be freely selected. I have a 3-phase system, so I have a 3-phase schematic, and just place the voltage and the current signals via drag and drop here. You already see a small preview of your data of your signals and your measured active power. As the system is not running at the moment, it's nearly nothing. And to determining the mechanical efficiency as well, I have a mechanical power group where I just need to drag and drop the engine speed and the torque signal. And then you have automatically created some channels which calculate the mechanical power, the running speed, the torque, and also the mechanical efficiency. And you see here in the channels list already very many different signals. For example, just the 2 RMS voltages, and all these channels here, I will not go through in detail about them now, but nearly any or very much parameters are automatically calculated, so you don't need to set up any power calculation manually by mathematics or formula, but all the power parameters are automatically calculated. So much for the power engine. And for determining the grid power, I have a second power group created here, which is now a 1-phase system, and I just drag and dropped also grid voltage and grid current here to determining the grid power and to do the electrical efficiency determination of the inverter. And to show you how the data is visualized, I go back to the measurement screen and start the engine. In the meantime, just press the start button now, and on this measurement screen you see the power calculation for the grid power. You see here the fundamental frequency of the grid, which is approximately 50 Hertz at the moment, and the active power on the grid side is approximately 42 watts at the moment. And on this side here you have the engine power calculated. So you see an overview about your power values for each phase separated, and also a total power consumption and a total power analysis of the system. The system is currently running with 60 Hertz fundamental frequency and consumes a negative power of up to approximately 21 watts at the moment, which leads to an electrical efficiency of approximately 54% at the moment. On the next measurement screen, I will show you, and I wanted to show you how the mechanical power is determined. So you see the electrical power analysis of the engine again here. You see the actual angle, rotational angle of your system here, and automatically calculated are the mechanical power of the system, which is approximately 18 watts at the moment. The running speed is 1720 RPM at the moment, and the torque is 0.1 Newton meters at the moment, which leads to electrical efficiency of approximately 85% at the moment. And last but not least, on the last measurement page, you see the raw data of your acceleration, of your airborne sound, and also the temperature acquired with one single measurement system, even if several measurement devices are used, but everything is set up with one single configuration file and also stored to one single data file. When we talk about test beds, you also need a possibility to control your measurement device from the test bed, and therefore I quickly want to show you how you can configure and control your system with a Skippy connection. I am moving now a small program which is able to send out Skippy commands to a measurement system. So this is just an exemplary program. Please just imagine this can be any test bed and look completely arbitrarily according to your user specific demands. This is just an example to show you how we can control a measurement device with Skippy commands. I will now just quickly connect to the system by entering the IP address and the port which is used for the connection. And you instantly see here on the measurement device that the remote connection is active. So I can, for example, just show you, I can remotely start the recording on the measurement device over Skippy remote control. So you see here that the recording has started on the system. I can, for example, also query the channel list and to show you how the data transfer is working with Skippy, I will quickly drag and drop the active power of the engine and the active power of the grid here to start the data transfer, and also the raw data of the temperature engine. I will transfer the data with 100 milliseconds, and then I just press the start button, and you see here how quickly and how easy you can transfer your measurement data from your measurement device to your test bed, and how easy that can be set up with Skippy commands. You can for sure also stop the data transfer again and stop the data recording as well, again, remotely from my test bed on my measurement device. So this has been also a quick and a simple, or a hopefully simple introduction into distributed power analysis, and a quick introduction or an example how a distributed power analyzer may be set up and look like in the real life. So thank you for your attention from my side, and now it's up to you to ask us some questions, please.
So thank you, Raphael, for your practical and theoretical explanation of what distributed power analyzers are for and what are their advantages. We got already 3 questions meanwhile, so I'm just going to read them as they are written and try to interpret what is meant with it, and I hope you will understand it. So the 3 questions until now are pointed towards you. So question number 1 is, we need to record raw data vibrations additional to power measurements. And yes, the raw data is necessary to make FFT analysis post-processing. Is this possible with the Tevatron measurement system?
Basically, yes. I already showed you here that we already acquire the vibrational data with the power, or with the system which also determines and calculates the power. You can for sure use this acceleration and this vibration data to do an FFT analysis in the post-processing, but I would recommend you, or I would also like to show you that you can even do an online FFT calculation with the acceleration data. So just all you need is the spectrum analyzer instrument, which I'm now placing at the measurement screen and adjusting the size a little bit, and search the acceleration channel in the channel list, which is this one. And you already see something happening down here. Just increase the size a little bit. And so I'm quickly adjusting this lines resolution, change the spectrum type to decibel, and use a logarithmic frequency scaling from 10 Hertz to 1000 Hertz. And this is how easy and how quickly you can also do an online FFT analysis, spectral analysis with your measurement device and with your power analyzer.
Perfect, thank you. Just to summarize it, so raw data is of course possible with our systems, and you have it available to do post-processing with it, but with our system it's not necessary because you can already do it online during the measurement. We have the tools in our measurement software.
Exactly.
Second question would be, how exact is the sync of a Tevatron?
That depends on the synchronization signal. When we use the internal sync source to synchronize several Tevatron devices, the absolute accuracy is plus minus 60 nanoseconds, plus 5 additional nanoseconds per meter. So when we have a synchronization cable length of approximately 8 meters, in between which should be realistic normally, we have an absolute accuracy of plus minus 100 nanoseconds. In the time domain, when we think about a phase accuracy and a phase error thereby, I'm just quickly calculating what the phase error may be when you have an accuracy of plus minus 100 nanoseconds. You have the 100 nanoseconds multiplied with 360 degree. And let's assume a fundamental frequency of 50 Hertz, for example, divided by 10 nanosecond, by 100, by 10 times 9 for respecting the nanoseconds, we have an accuracy of approximately 0.0, a phase error of approximately 0.02 degree for a 50 Hertz fundamental frequency signal.
Okay.
So absolute time accuracy of plus minus 100 nanoseconds, which causes a phase error of approximately 0.02 degree of 50 Hertz fundamental frequency.
Okay, thank you for that. Additional to that question was also asked, what external hardware is necessary to sync to Tevatron systems? Syncing additional hardware is always a pain.
When you only use Tevatron equipment, you don't need additional external hardware, because the Tevatron devices provide the possibility or have an integrated timing source integrated, and this timing signal can be output to clock several Tevatron measurement devices. When you like an external sync, because you also need to synchronize other devices as well, you it depends on the sync signal you want to have. So for example, when you use PTP as a synchronization source, you need a device which can create and generate a PTP clock signal to synchronize the Tevatron device as well. So you need a clock generator or a clock master when you want to use an external synchronization signal. But when it's just about synchronizing Tevatron measurement equipment, you don't really need additional external hardware, but just the Demeter devices.
Okay, thank you for that. We have a just dropped in question from the person who asked the first question. Is it possible to combine different signals during measurements, for example, with mathematic functions or whatever? So
yes, basically this is possible online and during the post-processing. I will just quickly show you this on the measurement device. You have the plus button here, and you see a powerful math library available. And to combine different measurement signals in a mathematical way, you have the formula module. Just press the add button. Formula is created automatically, and so you can, for example, add your your input voltages of the three-phase motor, for example, even if it does obviously not make any sense at the moment, but you could, for example, add them and just divide them by 3 to have the average signal or something like this. Obviously, this doesn't make any sense, but I hope this illustrates the possibility of combining several measurement signals, and you have different mathematical operations here available as well. You can do trigonometrical calculations. You have logical operators, different measurement functions for calculating or for counting the numbers a certain threshold is exceeded, for example, for determining the global minimum or the global maximum during the measurement, and also different functions for rounding your signals, for acquiring for having the measurement time available for further mathematical operations, and so on and so on. So this is also possible to do mathematical calculations online during data acquisition, or also offline during the post-processing of your data files.
Perfect. Thank you for answering those questions. I don't see any questions dropped so far. So if you still have any questions and or they appear later on after this webinar, please feel free to contact us via social media, email, or phone. We are there for you. We're going to put this webinar also on YouTube, so it will be available also for you to watch it afterwards. We have also published a white paper regarding this topic, or different other white papers, which are available on our homepage under Academy. There are going to be also further webinars in the future. Everything is combined under Academy on our homepage. Please stay just 1 or 2 minutes online after this webinar to answer a 3-question survey regarding the quality and give us some feedback so we can rise our quality of our webinar in the future. And that's all from our side. Thank you for participating, and I hope to see you soon in person. And yeah, thank you so much, and goodbye, and see you soon at the next webinars. Thank you.
Thank you. Goodbye.